So we're going to continue with our discussion of Chapter 1 and to get prepared for class number 5. So the topics for this class session we'll be looking at section 1-4, which is kind of a review of stoichiometry calculations that we learned about in general chemistry. Along with this, we're going to learn about an application in analytical chemistry called gravimetric analysis. So this is a type of analysis, a class of various methods that we can use to do analysis for certain types of analytes. And it gives us a good chance to practice some of these stoichiometry calculations. So what are we going to do? We're going to review reaction stoichiometry. We'll talk about stoichiometry calculations, solution stoichiometry calculations, limiting reagent, and finally a little bit on gravimetric analysis. So a reminder about balanced chemical equations. So because mass is conserved, and really atoms are conserved, we cannot create or destroy atoms in a chemical reaction, it turns out that the masses of the reactants and the masses of the products must be related in some way. And so what we can do, we can do this because we can count the atoms and molecules. And we call that counting of things and the relationships between counts of things. We call that stoichiometry. And it applies not just in chemistry, but to things like, recipes and cooking and building materials and so forth. So here's an example of a reaction. So this is the reaction between methane, CH4, and oxygen. So the combustion of methane, the principal component of natural gas. And anytime we combust hydrocarbons, we make carbon dioxide and water as products. So these stoichiometric coefficients here are telling you how many of these molecules are involved. So in pictures, here's a picture, a model of a methane molecule, and then there would be two O2 molecules. So the element oxygen exists as a diatomic molecule. And then, of course, the chemical reaction, what happens is we break bonds, we make bonds, the atoms are rearranged to produce carbon dioxide, and then two water molecules. Okay, so balanced chemical equations then tell us about the number, the counts of the molecules, and the coefficients are here to keep the reaction balanced. So remember, you always have to start out with a balanced chemical reaction, and hopefully you remember how to do that from general chemistry by inspection, by adding coefficients, and just keep on going back and forth until you get the same number of each type of atom on both sides of the reaction. So you see we have one carbon here, 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens, and so forth. So stoichiometry, we're going to think about that in terms of an analogy here. So it's kind of analogous to scaling up or down the amounts in a recipe. So sometimes you have a recipe for cooking and maybe you want to double it or triple it because you've got a lot of people coming, or maybe not as many people, and so you want to cut it by half or by a quarter. So how do you do that? How do you scale the recipes up and down? So for example, suppose we're making pancakes with a mix, and the box tells us to take 1 cup of mix, combine that with 3/4 of a cup of milk and 1 egg, and that's enough to make enough batter to make about 8 pancakes of a certain size. Okay, so we can write that as though it were a chemical reaction, right? So 1 cup of mix plus 3/4 of a cup of milk plus 1 egg yields 8 pancakes. So let's say we had a bigger crowd coming, or we were just really hungry and we wanted to make 24 pancakes. How many eggs would we need? So we can use the stoichiometry, these numbers, this relationship set up in this equation to tell us that in this recipe. So we're going to set it up as though it were a conversion problem. So 24 pancakes is what we have, what we're looking for, and we can use the conversion factor here that's set up in the stoichiometry of the reaction that says that for every 1 egg, we can make 8 pancakes. Okay, so 1 egg for every 8 pancakes that we make. And so doing the math, 24 times 1 divided by 8, well, and you probably thought of this in your head anyway. So, 8 pancakes, how many times does 8 go into 24? Well, 3 times. And so we're going to need 3 eggs. And so this, which is just a ratio of these different numbers, right, is a way that we can set it up to be a conversion factor. So you see that pancakes cancel. We do the same thing with a stoichiometry problem. So here's that combustion reaction again. And so we want to ask the question, so how many O2 molecules would we need right here if we wanted to make 5 carbon dioxide molecules? So you see the stoichiometry says that we make 1 carbon dioxide molecule for every 2 O2 molecules. So we're going to set that up just like we did the recipe problem. So 5 carbon dioxide molecules times is our conversion factor that we need 2 oxygen molecules for every 1 carbon dioxide molecule that we produce. And that's just from the reaction stoichiometry and looking at these coefficients that are in front of the molecule. Remember, we can't change these numbers that are subscripts because that's telling you how the molecule itself is put together, right? So we can't change that because then we change the identity of the molecule. So we can actually do this same problem not just with individual molecules, but by scaling this up using any counting unit. So these 2's and 1's that are in this equation, they can be molecules, but they could also be, 2 pairs of molecules or 2 dozen molecules, or more commonly in chemistry, moles, right? Because we work with very large numbers of these substances because molecules are so small. So we will use mole as a big grouping that we count. So this reaction says 1 mole of methane reacts with 2 moles of oxygen to yield 1 mole of carbon dioxide plus 2 moles of water molecules. And so we would set up the stoichiometry calculation in the same way, converting 5 moles of CO2 into 10 moles of O2. So that's how many moles of O2 we would need just by using the stoichiometry right here when we were counting molecules to get 10 oxygen molecules. So we work the stoichiometry problem in the same way. So oftentimes in stoichiometry problems, we're not given the problem in terms of counting of molecules or numbers of moles even. So oftentimes we're given them in lab scale units like grams or milliliters. So if we're not given amounts in molecules or moles, the first thing that we're going to have to do is convert, because the language of a chemical equation is all about counts. And if we're not given a count to start out with, we've got to figure out how to get there. So we know how to do that. If we're given grams, we can use the molar mass, a conversion factor, relates grams to moles, that ratio, to convert to moles, and a mole is a counting unit. Similarly, if we know how many liters of a solution we're using, we could use molarity, right? Capital M, moles divided by liters, is a way of converting between moles and liters, and that would let us go from liters to moles of some solute that's a part of that solution, okay? So we can use these 2 conversions that we already know how to do to get to that counting unit. Then we can use the mole ratios as before, just like down here. So we set up a mole ratio based on the chemical reaction, relating the chemicals that we're interested in. And then finally, we might need to convert those moles back into grams or liters if we need to know some sort of lab size information, depending on what the problem says. So let's do an example. So here we go. We're going to expand this problem that we've been looking at. So how many grams of oxygen are required to react with 10 grams of methane according to this reaction that we've kind of been studying? All right, so first we know that a reaction is in terms of a count, so we need to get that into a count unit like moles. So the first thing that we're going to do is convert grams to moles. So what are we given? Well, we're given information about the number of grams of this starting material, the methane. So we're going to convert those 10 grams of methane into moles. So we just divide by the molar mass of methane, so we'll calculate that off the periodic table. And you see that the grams of methane would cancel out by putting that gram unit in the denominator, and that tells us how many moles of methane. Now we can use the stoichiometry of this reaction to figure out how many moles of O2 we would need to make that much CO2. So we're trying to make 0.6233 moles of methane. Sorry, we have 0.6233 moles of methane, and we want to know how much oxygen we're going to need. So according to the stoichiometry, we need 2 moles of oxygen for every 1 mole of methane that we make. So now the moles of methane will cancel out, and we get 1.247 moles of O2. So that's how much O2 we're going to need. But we would like to know how many grams the question asks us about of oxygen. So we need to do a final step where we convert these moles into grams using the molar mass of O2. So there's 1.247 moles of O2, about 32 grams per every 1 mole, so 31.9988 grams of O2 in every 1 mole of O2 molecule. So again, the moles of O2 will cancel out, and that tells us how many grams of oxygen gas we would need to react with all 10 grams of methane that we have. Okay, so we've been able to think of things in terms of masses, but we had to go back to that sort of molecular level language of the chemical reaction. We can do the same thing when we're talking about solutions. So in this case, we have a reaction. We want to know how many milliliters of a 0.150 molar H2SO4, you'll recall that sulfuric acid. So how many milliliters of this 0.150 molar sulfuric acid are needed to react completely with 25 milliliters of 0.200 molar sodium hydroxide solution according to this reaction. So this reaction says that 1 mole of sulfuric acid molecules in the aqueous solution react with 2 moles of sodium hydroxide in aqueous solution. So we're just having 2 aqueous solutions, we're pouring those together. What do we produce? We produce 2 moles of water molecules. This should have been liquid phase. I forgot to add my phase label there. So minus a half point there for me. Plus Na2SO4, that's sodium sulfate aqueous, right? So that's our other product. So this is a classic acid-base neutralization reaction. We've got an acid plus a base yields a salt, sodium sulfate, plus water. All right, so there's our reaction stoichiometry. So we've got some reactions set up. We're trying to look at the relationship between H2SO4 and NaOH, and we see it's 2 to 1 according to the stoichiometry. But we were given information in milliliters, right? So we know we've got 25 milliliters of this sodium hydroxide, and it's actually a solution. So we've got a certain number of moles of this sodium hydroxide dissolved in water. And we want to know how many milliliters of this sulfuric acid solution we're going to need. So the first step, we've got to get into our counting unit here. We were given 25 milliliters, and we know molarity. So we know that molarity is a way of converting between liters or milliliters of solution and moles of a solute, and sodium hydroxide is our solute. So here we go. 25 milliliters of sodium hydroxide was our starting amount, and then we're going to use the molarity. So 0.2 millimoles of sodium hydroxide in every 1 milliliter of sodium hydroxide. So remember, molarity stands for moles per liter, but we can also think of this milli as canceling out. We can just insert that in there. So molarity is also millimoles per milliliter. And since we were given milliliters, it makes sense to use that unit. So you'll see that the milliliters of NaOH cancel out, and we know how many millimoles of sodium hydroxide we have, 5 millimoles. So that's how many millimoles of sodium hydroxide we have. Now we're ready to use the stoichiometry. So the stoichiometry says if we have 5 millimoles of sodium hydroxide, that we need 1 millimole of sulfuric acid for every 2 millimoles of sodium hydroxide that we have. So there's our 1 to 2 stoichiometry. So we take 5, we divide it by 2, we get 2.5. 2.5 millimoles of H2SO4 molecules is how many we will need, right? But we can't just go and count those out because we have a solution of that. So we need to know how many milliliters of that solution to take to get this number of millimoles. So our last step is going to be to convert these millimoles into milliliters. And you remember we can go between moles and liters with molarity. So millimoles and milliliters with molarity. So 2.50 millimoles, and what's the molarity of our sulfuric acid? 0.150. So in every 1 milliliter of sulfuric acid solution, we have 0.150 millimoles. And now putting that in the denominator, you see that it cancels out. And so we do the math here. 2.50 divided by 0.150 equals 16.7 milliliters of sulfuric acid. So that's how much sulfuric acid we would need to take to completely neutralize all of that sodium hydroxide solution that we had, that 25 milliliters of sodium hydroxide. All right, so our last topic, thinking about stoichiometry, has to do with limiting reagent. You will sometimes hear this called limiting reactant because in all cases the reagents are a reactant. But a reagent is just a fancy chemical word for something that you're going to mix together to do a chemical reaction. So we call those reagents. So you mix reagents to do a chemical reaction. So the limiting reagent then in a chemical reaction is whichever one is consumed first. So the analogy that is often used here is imagine that you're making sandwiches following a certain recipe. So you need 2 slices of bread, you need 1 slice of cheese, and 2 slices of meat. So depending on how much bread, cheese, and meat you have, you may have to stop making sandwiches because you've run out of ingredients. So one of those ingredients may run out first. So that's an example of a limiting reagent analogy. So once the limiting reagent is gone, right, we've run out of something that the reaction needs, and so the reaction stops. And that means we're going to have some excess reagent, and there may be more than one of them, so there may be several excess reagents that will be left over. So there's only ever one limiting reagent, everything else would be excess reagents. So as a simple example, let's look at this reaction. So we've got some substance A that's reacting with 2 moles of B to produce some product P, okay? So let's say that we mix 0.751 moles of A together with 1.43 moles of B. So which one of those is the limiting reagent? So you know you've got a limiting reagent situation when you're told the two amounts of some reactants that you have. Okay, so which one is going to be run out first? So according to the stoichiometry, we need twice as many moles of B as we have moles of A. Do we have that? Well, in some cases it's easy to see, in others it's not so much. So maybe we're going to have to do a calculation here just to prove to ourselves which one is the limiting reagent. So this is a sometimes helpful way to think about a chemical reaction. It's a little reaction table, and it's in terms of moles. All right, so remember reaction tables, we always want those in terms of moles. So this is I here with a period, and F here with a period. That stands for initial and final. So initial is before anything reacts. Final is after the reaction is done, has come to a stop. So here we write down our initial amounts. Initially we've got 0.751 moles of A, and we've got 1.43 moles of B, and 0 moles of P because we haven't made any product yet. And so finally, how much of these are we going to have? So one of them is going to run out. We don't know which one. So what we often do here is let's just pick one. Let's just say, hey, imagine that A were the limiting reactant. All right, so if we're going to use up all 0.751 moles of A, how many moles of B would we need to react with all that? And that's just like the stoichiometry problems that we talked about, here, right? So here we were looking at how many oxygen molecules are needed, to react with a certain number of methane. So same idea, but now we're going to do it with assuming that this is the limiting reactant. And so we set up the stoichiometry. So 0.751 moles of A is how much we have. And then we see from the stoichiometry that we need 2 moles of B for every 1 mole of A that we react. So we double this number. We've got 1.502 moles of B required. So this is how much B we would need to react with all of this A. But looking at how much B we actually have, well, we don't have that much, right? So that means that, in fact, B is our limiting reagent because we're going to run out of that. Because if we're going to react all of this, we would need this much. So we only have 1.43 moles of B, so B must be our limiting reactant. And so there's a quick way to figuring out what your limiting reagent is. Once you're in moles, just pick one and hypothesize that it's the limiting reactant and figure out how much of the other reactant or other reactants you might need. And that'll lead you to what the limiting reagent is. All right, then we need to figure out if B then is the limiting reactant, how much is required to completely consume A. So if B is the limiting reactant, all the moles of it will be consumed, so minus 1.43 to leave us with 0 moles at the end. By the way, I've added an extra row into our reaction table here. So this is for initial, and this is my abbreviation for change. Okay, so initial, change, and final. All right, so if we have 1.43 moles of B, how many moles of A actually react? Well, according to the stoichiometry, we react 1 mole of A for every 2 moles of B, so we just divide 1.43 by 2, and that tells us that 0.715 moles of A are going to react with B. All right, so what's our change going to be here? It's going to be minus, because we're losing that number of moles, 0.715. And we just do the math down the column. So 0.715 minus, 0.751, man, that's confusing if you're dyslexic, right? 0.751 moles of A minus 0.715 gives us this number when we're done, just by doing the subtraction. So that's how much leftover A we would have, and we would completely run out of B. And then we could also, if we wanted to, predict how many moles of P would be formed. And in that case, we would just take our 1.43 moles of B, multiply it by 1 mole of P for every 2 moles of B, we would get the same answer. So we're going to make a positive, over here we'd make a plus sign, 0.715 moles of P, and that's how many moles of P we would have when the reaction is done. So when the reaction is done, we would know the final amounts, the amount of product, the amount of B, well, it's limiting reagent, so it was all used up, and the amount of A that was left over, 0.036 moles left over. Okay, now switching gears a little bit, let's talk about this analytical method. So this is a class of methods. It's called gravimetric analysis. That's called gravimetric analysis. You might think that this word kind of relates to gravity, and you would be right because it involves the measurement of mass. So there are two different styles to gravimetric analysis. One would be a direct analysis. So imagine that you have a sample and it's got several different components to it, A, X, Y, and Z. And let's imagine that A is our analyte. And so we want to know, well, what is the mass percent of A in our sample? Well, here's how we might be able to do that. Maybe we know some way of separating A out from the sample. So we can simply have our special technique that allows us to pluck A out of the sample, and then once we've got A, we just put it on a balance and we measure it. If we've measured the initial mass of our sample, then we just take the mass of A and we can find the percentage of A in our sample. So mass of A divided by the original mass of the sample would be the ratio of the part to the whole, and then we multiply by 100, and that would be the percentage composition, the weight percent of A, right? So we need to know the ratio of the part to the whole, so we need to know the mass of A divided by the mass of the whole sample. How do we find the mass of A? Well, we separate it, and we weigh it. We just put it on the balance. So it's pretty rare to find a system that would do that, but as an example, this is kind of interesting to know, but some breakfast cereals that are iron fortified breakfast cereals, so iron is an important nutrient because it's an important component of red blood cells that transfer oxygen. So if you're deficient in red blood cells or you don't have enough blood volume in your body, you become anemic, and that causes some problems. So anemia is a low red blood cell count with not enough iron perhaps in your blood. So some people eat iron fortified cereals to help with that. And interesting, cereal manufacturers put that iron into the cereal as metal filings. So they're actually little pieces of metal that are ground up and mixed in with the cereal meal and processed into flakes or whatever. So we can extract that iron because iron has an interesting property. It's ferromagnetic, so it reacts very strongly to magnetic fields and sticks very strongly to a magnet. So what we can do is take breakfast cereal, dump it into a big beaker with a lot of water, whirl it around in a blender. Well, you'd put it in a blender first and make this big slurry, so you have to break up all the stuff and get it in the water. And then you pour that into a big beaker and you put a really strong magnet on the bottom of the beaker, and then you stir everything around in there and just pour off everything else, and you'll see that at the bottom of the beaker, wherever the magnet is, there will be iron stuck to the bottom of the beaker or the side of the beaker with the magnet on the other side of the beaker, for example. And then you can just transfer that iron, those iron filings off, dry them, and weigh them directly. So that would be a direct gravimetric analysis. More commonly, we do a gravimetric analysis that it's indirect. So we're not actually measuring the analyte directly. We're measuring something that is related to the analyte. And we do that based on a selective precipitation reaction. You'll remember that a precipitation reaction is a reaction when we take two liquid solutions and we end up forming a solid. It makes the solution go all cloudy and opaque, and then we can filter or centrifuge that solid down. So in this example, A is our analyte. It's dissolved in water. So we've got, let's say a clear solution. And we're going to add to that a precipitating agent. So I call that P. It's also dissolved in water. We're going to kind of add an excess of this so that our analyte is our limiting reagent. So we want to make sure we use all of that up. And so we're going to add some P to that. And what happens is we end up making a solid, S. So S for solid in the solid phase, that's our precipitate. And there may be some other products here that are left over from this reaction too. So I just left that there. So we're interested in what is this solid, right? So that solid is related by the stoichiometry in my reaction, 1 to 1, but it may be a different stoichiometry depending on how that reaction gets balanced. So what we can do now is recover this solid by filtration or some other means, but filtration is typical. So in this case we have a funnel. The funnel has a perforated plate down at the bottom, and we put filter paper on top of that. Then we kind of stir that solution all around so that the little chunks of solid are suspended in the liquid, and we pour that into our funnel, making sure we get every last bit of solid washed into there. And then air pressure, perhaps with vacuum pulling down here, is going to pull that liquid through the funnel, but the solid will be remained on the filter paper. We can then remove that filter paper, or maybe take the top part of the funnel off, put it in a drying oven so that we remove all the water that's part of the solid, and then we can simply weigh that solid. Now the mass of the solid, right, is not the same as the mass of the analyte, But we can do stoichiometry to figure out, hey, if I know the mass of the solid and I know this chemical reaction, I can work backwards to find moles of the solid, then moles of A, and then how many grams of A I had. And that's summarized in this table, the indirect gravimetric analysis calculation scheme. So we measure the grams of S on the balance. We convert to moles of S using the molar mass of S, right? Then we use our precipitation reaction stoichiometry. So in my example, that was 1 mole of analyte for every 1 mole of solid that you get. But your reaction, if you were doing a precipitation reaction, might be different than that. So we use the stoichiometry to convert moles of S into moles of A, and then finally, because we know what A is, we know its molar mass, and we can go from moles to grams using the molar mass of A. Then finally, once we know the grams of A, we can figure out a concentration unit, right? What is the mass percent, the weight percent of A? And so that's just a ratio of part, the grams of A, to the whole, the grams of the total sample that you started out with, right? So we were back here at one of these pictures, the total sample. And then we multiply by 100 to convert that into a percentage. All right, so there's another example of how we can apply stoichiometry in a gravimetric analysis. So that's it for this class. We'll be working through some example problems in the class session, so bring your questions if any of this is confusing, and we'll do some more example problems during class. See you in class.